Okay, we're talking about function operations in this particular lesson. Um, for instance, we are dealing here. I'm going to turn this camera just a little bit. Okay. Um, we're talking about function operations, addition of functions. We can add functions together. We can multiply. We can subtract. We can divide. All of this notation is showing you that if they talk about f plus g, that's the same thing as if they talk about f of x and g of x. This is that weird Euler's function notation. Euler was the man they named it after, right? Because he's the one that came up with it. Function notation. This is just a fancy way of saying y, and we do that so that we can separate different equations. So what we're showing you with all these properties is that you can multiply, subtract, divide. Everything is exactly the way you think it should be. The notation is not trying to mislead you in any way or isn't confusing. So let's just take a look at an example here. I've got these two functions, f of x equals 3x plus 8 and g of x equals 2x minus 12. We're going to start by adding the two functions together, f of x plus g of x. So that would be 3x plus 8 plus 2x minus 12. And yes, it is as simple as combining my like terms. So that would be 5x plus, minus 4. 5x minus 4 in this case. 8 minus 12. So that's the addition of the two, right? That's f of f plus g. F minus g, f of x minus g of x. It is really important that you get them in the correct order. 3x plus 8. I can't even write. 3x plus 8 minus 2x minus 12. Distributing the negative 1. I'm off screen there. Distributing the negative 1 gives me 3x plus 8 minus 2x plus 12. 3x minus 2x is 1x. 8 plus 12 is 20. So this is the difference between the two. F of x minus g of x equals x plus 20. Now, is there any number in the universe which you cannot multiply by 5 and subtract 4 from that? The answer is no. So when it comes to domains, the word domain is all the possible x values which would make this true. So the domain for this would be all real numbers. All real numbers. Now, if you want to get fancy, you can use a double bar like this, an R, a capital R with this double bar, and that means the same thing as all real numbers. That's the symbol that we use in many upper-level math classes for all real numbers. Is there any number in the universe which you cannot add 20 to? So I guess the domain for this one is also all real numbers. So we're going to be asking you, not only can you add and subtract, multiply, and divide, but do you know what numbers are possible for x? So we have this next situation. I just thought I'd add another one in there. Two different functions, f of x and g of x. You're always going to have to start out by knowing what f of x and g of x are. We will give those, the test or the quiz question or homework, we'll give those to you. Otherwise, you won't know what to do. So I want to add these two equations together. So we've got f of x plus g of x. Not too terribly complicated. 5x squared plus 1x plus 1. Question in the, this is f plus g right here. Is there any number in the universe that you cannot square, multiply by 5, add to the original number, and then add 1 to? The answer is no. So the domain for this one is also all real numbers. The only problem on domain we're going to get into is when we get to the division questions. So don't think it's all real numbers for all of these. Multiplication. Can we multiply these two things together? We got f of x times g of x. Here are the two formulas. Okay, so we're going to multiply them together. X squared minus 1 times x plus 1. Wow, that looks kind of familiar from stuff from last chapter almost. As you know, I would probably do, I'm going to use a box. X squared times x is x cubed. X squared times 1 is x squared. X times negative 1, negative x, and negative 1 times 1 is negative 1. So the product is x cubed plus x squared minus 1x minus 1. That's f times g. Now, domain. Well, let's see. Is there any number you can't cube? Add to the original number squared, subtract the original number from, and then subtract 1. Nope. So that domain is all reals. As I said, we're not going to get into any problems until we get to this next example, the division question. So we end up with x squared minus 1 over x plus 1. Well, if I were you, I would factor the numerator. I see it's a difference of squares, so I'm going to factor it. I've got x plus 1 in the bottom. Is there any factors that cancel out? The answer is yes. There are two factors that cancel out. So f of x divided by g of x is equal to x minus 1. The question is, what about the domain? It is not all real numbers. Clearly, there's one number in the universe which is a problem. What number can you plug in for x right here in the denominator which would cause the fraction to kind of blow up on you? The answer is negative 1. So x can be any number in the universe except negative 1. If x is a negative 1, then the whole fraction is dissolved because it's no longer valid. You can't divide by 0. So negative 1 would cause 0 in the denominator. Okay, next example. Something else we're going to talk about, composition of functions. This is not multiplication. Composition of functions is not multiplication. Several of you are going to ignore me, and then you will end up with thinking it is multiplying. Okay. There are two different types of notations. You're going to see F, and then this little circle, and we read that following. F following g of x. Now, I never write that notation. I don't like that notation. I hate that notation. But it means the same thing as f of g of x. So, you know, if you're at a party and you're trying to read this like on a t-shirt or something, or maybe a billboard or commercial, TV commercial, f of g of x is how we read that. That is the preferred notation, and I'm always going to use that on my quizzes and tests. And what we're doing is we're putting one function inside of the other function. So it's a composition, not a multiplication. So for instance, when you see a situation like this, you've got two functions and you're being asked for g of f of negative 5. The first thing we want to do is figure out what f of negative 5 is. So start with that part. What is f of negative 5? F of negative 5, well, if I use the formula, that's negative 5 minus 2, or negative 7. So this question right here is really about g of negative 7. And g of negative 7, that's negative 7 squared, or 49. Now, does it work the same way if I switch the letters? Well, start out figuring out what g of negative 5 is. G of negative 5 is negative 5 squared, which is 25. So this question is really the same thing as f of 25. Well, that's 25 minus 2 according to the equation right there. So that's 23. 23 clearly does not equal 49, so they are not the same. You can't just switch these things around and think that you're going to get the same value. You must do them correctly. So start with the inside, figure out that part. Once you figure out that part, plug it into the one on the outside. It's kind of like the idea of innermost parentheses and working your way out. Okay, so we've got our two other equations, and now we're going to do something a little bit more complicated, the composition using a letter instead of a number. Use the one on the outside and look at what it says that you're doing to every value that you put into it. The f function in this case says whatever you plug into it, subtract 2 from it. So f of g of x says whatever you put into it, you're going to subtract 2 from it. The big question is, what are we going to plug into it? We're plugging in g of x. Well, g of x is x squared plus 1. Now, we're going to take that expression and subtract 2 from it. Those parentheses really don't matter in this case, so that becomes x squared. 1 minus 2 is negative 1. So here is f of g of x. Will that be the same as g of f of x? Well, what is the g function, the one on the outside? What does it tell you to do to all the values you put into it? Well, it says square the value and then add 1. So we're going to leave a parenthesis squared plus 1. What are we putting into this g function? We're putting in this entire expression f of x, which is x minus 2. Now, keep in mind that you are, anytime you're squaring something, that you're a binomial, you are foiling it, so that you're ending up with x squared minus 4x plus 4 plus 1. X squared minus 4x plus 5. That's g of f of x. Clearly, f of g of x and g of f of x are not the same thing. There are occasions where it is true, but not always. Last example is example 4. Sorry, I scribbled out a few things here, but we have a rebate and a discount. We're at the store and we have a rebate of $5, and we could get a discount of 80% or 20% off. And if you're getting a discount of 20% off, that means you're going to pay 80%. So is there a difference on when they are given? Whether you give the rebate first and then the discount, or the discount first and then the rebate? So f of g of x, the f of x function, the one on the outside, says whatever we are doing, we're going to subtract 5. So obviously this is discount first, rebate second. Discount first, rebate second. Not a whole lot of simplifying can happen. There it is, 0.8x minus 5. Well, let's see here. What happens if I reverse the process? In other words, the rebate first and then the discount. So the discount of 0.8 times whatever you put into it, and we're putting in the x minus 5. A little bit of distributing happens here, so we have 0.8x minus 4. Is there a difference between these two? You better believe it. This one is $1 cheaper. So you definitely paid more if you did this option. Don't think that marketing people don't realize this, folks. The order in which they switch things around, they're going to put it in their favor, not yours. So there's a composition of two functions, and you can clearly see that in one situation you're going to pay more for the item than the other. Be in class.